In this tutorial, I'm going to talk about a mass that is being pulled by a rope at an angle with the horizontal. This is Physics is Easy with Mr. Jesse. A crate of mass m is pulled by a rope at an angle theta with the horizontal. The crate moves horizontally on a frictionless horizontal plane. The tension in the rope is F. So this is our situation right here. So before we would answer this, the questions 41 and 42, let us first draw the free body diagram of this crate that we have in our problem. So the first thing that we need to do is to identify the forces that are acting on the crate. So we have number one, since the crate is on the ground or is on a plane, so there should be normal force. So normal force is the force that is exerted by the surface at which an object is in contact with. So that's gonna be normal force. The next force we have, of course, we have the force of gravity, or we could just say the weight. And we also have the applied force, or in this case, that's actually tension, and that is labeled with an F. So to draw the free body diagram, let us just depict or illustrate the crate as a dot. So for example, this is our crate right here. That's our crate. The forces acting on it would be the normal force, which is directed upward. That's the normal force. It's perpendicular to the surface at which the object is in contact with. And we also have the weight. So that's directed down. And then we have the tension or the force, which is this. Alright, that is our force. Now, since this tension F is oriented in between the x and the y axis, it is very important to break it down into components. So this force F here has the x component, which is that. I'm going to call that Fx. And a y component, which is this. I'm going to call that Fy. So once again, this one right here is Fx, and this one here is our Fy. Now let us write the Newton's second law of motion that is related to this particular problem. So we start with the F net along the y-axis. So we say F net on the y-axis would be equal to the mass of the object multiplied by the acceleration of the object along the y-axis. So F net y would be the forces that are on the y-axis. So we have the normal force, it's directed upward, so that's going to be positive, minus the weight, that's because it's directed downward. And we also have the y component of F, so we have Fy. So let me write that down. So that's going to be plus Fy because that is directed upward. And since our object is not moving up or down, so therefore that's just going to be equal to mass multiplied by 0 because the acceleration is 0. The object is not moving in this case. So rewriting this, we will have the normal force is minus the weight of the object plus the y component of tension, that is equal to 0. And now let us write the F net along the x-axis. So we will have F net along the x-axis is going to be equal to the mass multiplied by the acceleration along the x-axis. Alright, now the forces along the x-axis would just be equal to Fx, and that's it. We don't have any friction because according to the problem, that is in fact frictionless. So the only force that is on the x-axis would be the x component of tension, and that is equal to the mass multiplied by the acceleration. And since we could clearly infer that the object is going to move to the right, so the acceleration here is going to be positive. Now for question number 41, we're interested to solve for the acceleration of the crate. So we have two equations here, the one for y component and the one for the x component. So obviously we should be using this equation because this is where we could find the acceleration a. So in fact, in solving number 41, we could just say fx. So number 41, let me write that here. We have the x component of tension is equal to mass multiplied by the acceleration. Now, what is the x component of the tension? To answer that, let us look at this diagram right here. So, if you notice, this actually forms a right triangle, and the angle is found right there in the middle of that right triangle, which is this. That's our theta. Let me just change its color so that it's going to become clearer. Okay, so we are given f, and we are interested to solve for fx. So let us try to express fx in terms of the given, which is f. So this fx right here is the adjacent side with respect to this angle theta. So we have the hypotenuse and we have the adjacent side. So in fact, we are going to use the cosine function. So recall that cosine is equal to, or cosine theta is equal to adjacent, the adjacent side over the hypotenuse. So we have cosine theta, the adjacent side is equal to fx. So once again, this is our angle. The adjacent side is the side that is beside that angle, divided by our hypotenuse. So in this case, our hypotenuse is our f. So therefore, we could say that fx is in fact equal to cosine theta multiplied by the force f, because as we manipulate this equation, we could multiply this with f, we could multiply that with f. We will be able to cancel the f on the right side of the equation, so we will have fx is equal to cosine theta f. Now, having said that, we could substitute now our fx, which is cosine theta f, to the original equation, so that we will have, instead of fx, I'm gonna write now f cosine theta. Again, they are just actually the same. It's just equal to f cosine theta is equal to the mass of the object, or mass of the crate, divided by the acceleration. And since I am interested to solve for the acceleration, I'll just have to divide both sides by the mass. Divided by the mass, I will be able to cancel mass on the right side of the equation, so that the acceleration is equal to f cosine theta divided by m. And that is the answer to number 41. And now let us proceed to question number 42. What is the magnitude of the normal force acting on the crate? So to solve that, we have to go back to the equation that we had earlier that has the normal force, and it is this equation that we are going to use in order for us to be able to solve this problem that we have in number 42. Okay, so let me minimize that. Right, rewriting question, or rewriting the equation that we need for number 42. So for number 42, we have the equation n minus the weight of the object plus the f component of our tension is equal to 0. So we are interested to solve for n. So we just have to express this equation in such a manner that n would be on one side of the equation and the rest of the variables on the other. So I will have n is equal to, I'll be transposing weight to the other side, as well as this the y component of tension, so that I'm gonna have negative weight minus fy. Now I am going to expand w and fy. So weight is just equal to the mass of the object multiplied by the acceleration due to gravity, and the the y component of the weight, or rather the y component of the tension f, is just equal to, so let's look at this figure once again. We have the angle, we have this angle right here, and this is the y component of the weight, and we are given, rather, y component of the tension, and we are given tension F. So this is the opposite side with respect to this angle. That's the opposite side. And this one right here is the hypotenuse. So we have the opposite side and the hypotenuse. That means we are going to be looking into the sine function, because remember that if we have sine function, let me write that on this side, sine theta is just equal to the opposite side divided by the hypotenuse. So we will have the sine theta, and in this case the opposite side to our angle is going to be Fy. So I will say Fy divided by the hypotenuse, which is F, and therefore Fy is just equal to F sine theta. Again, I'll just have to be multiplying both sides by F so that I will be able to express this equation in terms of Fy. So as a matter of fact, my Fy is, this Fy right here is equal to F sine theta. So let me write that down. Fy is F sine theta, and that is equal to the normal force that question number 2 is asking for. So we have solved the problem for question number 42, and that is letter E. And that concludes this lesson. Always remember, physics is easy with Mr. Jesse.